Good afternoon. My name is Keely Calhoun, and today we're going to be talking about X-ray crystallography. Before we get started, I'd like to touch on some of the learning objectives for this presentation. First, we'd like to ask what is X-ray crystallography. Then, we'd like to address what its origins are. We'd like to address how it works, and then what some of the applications for X-ray crystallography are. First things first, let's address what X-ray crystallography is. According to the Merriam-Webster Dictionary, X-ray crystallography is a technique in which X-ray diffraction, the patterned way X-ray light scatters when fed through a sample, is used to get information about the identity or structure of a crystalline substance. Before we jump into how X-ray crystallography works, I'd like to talk a bit more about the origins of this technique. So Max von Laue was part of a great number of physicists of his time who were trying to determine the nature of X-rays. He wanted to see how he could apply what they knew about X-rays at the time to understanding crystals. They suspected that atoms were capable of coming together to form a crystal lattice structure, with the distance between each atom in this structure being about 1 angstrom, or 10 to the negative 8 centimeters, apart. He noted that if X-rays were indeed electromagnetic radiation, which has a much smaller wavelength than light, X-rays would be in the same order of magnitude as the space between atoms. So he postulated that the atoms in these structures could diffract X-rays the way that we see an infrared spectrometer diffract infrared light. His colleagues, Walter Frederick and Paul Knipping, conducted an experiment that ended up providing supporting evidence for his hypothesis and the theory that crystalline solids have a repeating structure. They were able to record the diffraction pattern of the X-ray radiation of copper sulfate pentahydrate in their experiment. Alrighty, on to the most important part. How does this technique work? So, X-rays are high-energy waves with short wavelengths, which allow them to bounce off of atoms within a molecule without being absorbed. The rebound of these waves are what create diffraction patterns. If we look at the image provided, we see that X-rays are produced by electrons striking a copper anode and are fired and focused into a parallel beam using a slit plate. The crystal sample is mounted in the beam's path and rotated, while a shield keeps the source beam from throwing off the sensitive photographic plate's recordings. It's worth noting that until the last decade, X-ray film was used in imaging these diffraction patterns. In more recent years, advanced imaging plates and software that can connect directly to machines for data analysis are being used. From these diffraction patterns, scientists are able to detect interference between X-ray waves, symmetry in the packing of the crystal structure, and the size of the repeating units of the lattice as the waves scatter on the atoms. The size of the diffraction spots can also indicate structure factors that are used to compile maps of electron densities. Computers then analyze patterns to shape the suspected molecular structure of the sample. Though some limitations are present, while clearer crystals make for a more accurate model, impurities can skew data or make diffraction patterns muddled. A crystalline lattice is required in order to obtain a legible diffraction pattern, which is hard to precipitate with some larger molecules and their structures. One of the most significant applications of X-ray crystallography was when it was used to image the helical structure of DNA. Today, we continue to use this technique to find the structure of larger and larger molecules, like those we use in pharmaceuticals or for the complex proteins within our bodies. Knowing the structure of these molecules allows us to have a greater understanding of their mechanisms as well as their purpose. As ability to process diffraction patterns has grown over the years, the science dedicated to crystal purification and growth has proliferated. Scientists are now looking at taking crystal farming to space in order to better understand the effects of zero gravity on the ability for the most complex of molecules to precipitate into crystals. So let's revisit our learning objectives. X-ray crystallography is a technique to analyze diffraction patterns and determine the structure and identity of crystalline substances. Its origins come from the questions posed by von Laue and the experiments of Frederick and Knipping, who were trying to understand the nature of X-rays and the behavior of electromagnetic radiation. It works by creating and focusing an X-ray, which passes as a beam through a suspended crystal, whose diffraction pattern is shown on a photographic plate behind it, and then its meaningful applications are through the imaging of large molecules that often have a substantial biomedical or biochemical use, usually enzymes. This presentation was put together by myself for my Molecular Transformations course. The entire bibliography can be found in the notes of this video or in the supplemental Word document submitted.